I first want to just briefly review a little bit about the rules of thumb that we developed last time. So there are two main differences when we're talking about new physics being produced from colored particles versus electroweak production. And those two main differences come from the factorized cross-section. They depend upon the PDF side of this, so at what point different PDFs dominate. So if you have new colored particles and you're in a low X regime where you can produce the particles, you can add the glue-glue PDFs, and that really can change the rate by quite a bit. Of course, if we're talking about heavy new physics comparatively, if you go out to large X's where valence quarks dominate instead of C quarks, then you're basically playing the same QQ bar production game as you're doing for colored or electroweak particles. So then the hard matrix element's the only thing that matters, and you get about a factor of 100. And this translates into roughly a few hundred GeV difference for talking about electroweak final states versus colored final states in the reach at the LHC. However, this isn't the whole game, of course, for finding new physics. The thing that you really want is you need to not only have the rates big for the signal, but you need to have the rates for the signal much larger than your background so you can in principle see something. And this is determined not only by the cross-sections, but also by the efficiencies and the acceptances. So you want your signal efficiency, cross-section acceptance to be big, your backgrounds to be small. And for the case of colored particles, you can play this game a little bit because you have the extra factor in cross-sections, so you can still have a little bit of cross-section left over by going to higher mass scale separations, so you can get a separation between your signals and backgrounds. Unfortunately, this wasn't the case for electroweak production in a lot of the regimes that we talk about. If you want to have the largest cross-sections, you're sitting inside kind of the cross-sections for electroweak pair production of vector gauge bosons as well as top quark pair production. And these large cross-sections, when they become comparable to the background cross-sections, they're both at the electroweak scale. So you're talking about producing particles around 100 GeV each, and these particles, unfortunately, are around 100 GeV each. So there's not that many different cuts you can place to get a nice kinematic difference between the backgrounds and signals. So unfortunately, the bounds for electroweak particles are not nearly as useful as colored particles, which is unfortunate because these things probably have the most to say about the physics of the electroweak scale, of course. Colored particles are a complete add-on. In supersymmetry, they come for a reason, but if you want to go start model building with colored particles, feel free to, but it really might have absolutely nothing to do with anything with respect to electroweak symmetry breaking or lots of the interesting things out there. So the status of the LHC, the pre-LHC, was bounds on generic colored particles if you have missing energy in the events. Is about 300 GeV for the Tevatron and 100 GeV for LEP. And the LHC advanced this in the last year, so including the most recent results using 20 inverse femtobarns. It's now the TeV scale for colored particles that have missing energy, and about the 300 GeV scale for electroweak final states. Now, this scale is kind of ubiquitous for all new physics searches, even including things where we don't have missing energy. This is because this is basically where you start running out of rate at the LHC. So if you have a final state that you can identify and separate it from background, this is the scale for colored particles. This scale, it just got updated, as I said, over the last year or so. You can reach the 300 GeV scale for electroweak final states, but it's not the whole story, okay? There could be things literally sitting right around the corner at this electroweak energy scale. In fact, we could be sitting on top of many things, and we just don't know because we haven't become quite sensitive enough. So the biggest example you should think of is the Higgs, okay? I mean, we talk about the scale of supersymmetry being pushed off to the TeV scale, of course, but the Higgs was just very recently found. And the reason for this is because it's produced with an electroweak cross-section, and its final states are decaying to things like pairs of W bosons, pairs of Z bosons. And also with the advantage of the Higgs, even though we saw this already, you knew exactly what you were looking for, okay? Experimentalists were keyed on this beyond anything you can ever imagine. I mean, in terms of, if you talk about how the Higgs was found in the diphoton channel, I mean, they already have talked about what polynomials they wanted to fit. They did this in a million different ways. They knew exactly what the signal is, so you can find this. So it's very plausible, even though you always sound sometimes pessimistic after experimental talks that we haven't found anything so far. It's very plausible something could be sitting right at the electroweak scale that we haven't discovered quite yet. okay, just because of the fact that we're missing the cross-section and it looks like the kinematics of the backgrounds that we're talking about. Other examples of this that could be just right around the corner, there's the long-standing anomaly of the forward backward asymmetry at the top at the tevatron that D0 and CDF both see. I think Catherine Zurich will probably talk about this a little bit more in her lecture, so I won't go into this. But there's lots of things that could be sitting right here at the actual electroweak scale. And I think this is really what the importance of looking at things at the LHC should be kind of structured in this way. This is exactly the opposite way almost of how it was structured when I was here 10 years ago. The first thing you always did was you had this beautiful theoretical idea that you wanted to solve the hierarchy problem, or you wanted to solve something in flavor, you wanted to do something like this. You made your beautiful model, and you looked at all the consequences of your model, and you said, okay, at the LHC, when it turns on within 5 inverse femtobarn, we're going to see this, and that's the end of it. And you still should spend your time on this. But the other thing you have to keep in mind is the one new thing that we've actually found at the LHC so far is the Higgs boson. And if we really want to test the structure of electroweak symmetry breaking and see if we understand what's going on, we really want to look at the things that are most strongly coupled to electroweak symmetry breaking. So the top quark, of course, is the thing that's most strongly coupled with a coupling of order 1. But keep in mind, the electroweak gauge bosons are coupled to the Higgs with proportional to G weak, which you can say is about 2/3 or 1/3, so they're not really losing out a lot compared to the top. So you really want to make sure to focus on all of these three things, kind of the holy triumvirate of what the next running of the LHC will be, understanding these kinds of processes. So where do you look for new physics? And if some of you aren't quite familiar with doing this as of yet, you're still early in your graduate careers, the thing that you need to become very familiar with is both the Atlas and CMS Twickies. Okay? This is something that you should have bookmarked. You should know all the various different ways to get around this. And the beauty of this is that both CMS and Atlas are organized into a framework where they have various different physics groups searching for different things. So for instance, we care mostly normally about Higgs physics or supersymmetry, so you've heard a lot about those already, so you go to those groups. And unfortunately, lots of these other groups don't get a lot of play. So for instance, if you want to talk about QCD and understand QCD and some of the harder regimes, they have an entire group looking for measurements based on forward and small x QCD physics. There's B physics and quarkonia. I actually kind of find it interesting. If you kind of drew a bell curve of interest, I think it peaks around here and then drops off on both sides. I don't know if that's why they ordered these groups in that way. But the important thing is that this group here, this standard model physics and top physics, you really should take some time trying to understand the measurements that the LHC is doing and what goes about into these things. Now, I want to give a word of caution. You shouldn't just go to these Twickies and look at all the results, and you should just say, hey, I see a bin that's off by a little bit, and I'm going to spend the rest of my graduate career working on this. If you remember in the discussion section, Nima proposed the exercise of generating a bunch of Poissons in Mathematica and seeing what little bumps look like. So don't just spend all your time looking at these Twickie pages and trying to find out what these things are. But I really encourage all of you to spend some time looking at the measurements the LHC has made, not in the new physics categories. Understand what it's done with the standard model. It's amazing to figure out what things that has actually been measured by an experiment and what things we take for granted as knowing what the structure of the standard model is. There's a big gap in some of these areas. Now, of course, this doesn't mean you just forget this and you wait for New York Times to write an article about seeing the particle. You should take the time to look at these things and try to find these things. And of course, with the New York Times writing articles, if any of you guys were looking at the Times yesterday, also don't trust their science section either, because we had this nice faster than light article yesterday. But, but today's lecture, what I want to do is take you through a particular example. So there's a measurement that I talked about at the end of the day yesterday that was done by both Atlas and CMS. And I want to discuss the interplay between theory, experiment, and new physics. Okay? So this will give us an example of where there's been new theory calculations that have been done based on this because of a slight discrepancy. New experimental measurements were actually done because of new physics ideas that were put forth by myself and others. And you can kind of see how this sort of points us in the direction of how we can understand the standard model better at the LHC. Now, I want to emphasize the caveat. This can all be completely wrong, but I want to give you an example of how these various different pieces work together. What are some of the things that you might have to take to understand these things? And really the remarkable thing is this is going to be kind of one number that I'm going to talk to you about explaining. But inside this one number has all these different pieces of physics, okay? So I'll talk about supersymmetry, I'll talk about G-2, I'll talk about dark matter. But at the same time, if you're more on the QCD side of the physics, you need to understand things like resummation and higher order calculations and the differences between, so as Jesse talked about, resumming these logs. There's different types of logs that you have to resum and different sorts of ratios in these logs you can get depending on the process. So one simple number that an experiment lists, okay, just like the cross-section for a particular process, there's a huge amount of physics and a huge amount of physicists all devoted to understanding this. So there's a lot of meat in here. So I want to kind of take you through this. But hopefully you can understand how also the result of this is how you can understand, for instance, the impact of new physics can actually be gauged by theorists. And I'll show you an example at the end of how theorists, like you in this room, can actually find things or set new limits before the experimentalists can get to this. And it's an important interplay I think we have to have because unfortunately you hear statements, maybe I think Sunil mentioned the fact like there's 3,600 people on Atlas and sometimes little mistakes can get over in there now and then. But also at the same time, even though you have these order thousands of people on Atlas and CMS, they're really manpower limited in many cases. If you want to find something, you're only going to find like, let's say your handful of experimentalists you really trust. So really understand that you can make an impact in the LHC air. So as I said, the first place that you want to look if you want to understand things coupled to electroweak symmetry breaking and you want to understand electroweak production, the first thing that you can do is look at, for instance, one of the summary plots from Atlas or CMS talking about how well they actually understand the cross-sections at the LHC. So I showed you yesterday the plot from Sterling where he had compiled all the various different theoretical cross-sections, but here's an actual measurement of all the various experimental cross-sections. Now this is from Atlas. Atlas hasn't updated this in a while, but kind of gives you an example of what they're doing. So they care about single gauge bosons, they care about top quarks, and they care about diboson measurements. And as you see here, there's also a hierarchy in terms of the scales of these cross-sections. If you have something that's depending upon W and Z gauge bosons, this is a gigantic 10 to the 5th cross-section. That's why the backgrounds are very dangerous from these things, and you're probably not going to affect these in any significant way that you're going to see something. So if your only chance of seeing something is in single W production, good luck. Out here, though, you can start to see that these cross-sections actually are the same sorts of cross-sections that we talked about for new physics. The scale of these diboson productions of order 10 to 100 picobarns, and for instance, the cross-sections that we were talking about or 1 to 10 picobarns when we get to the LEP limit of 100 GeV or so. So these cross-sections are right around the same scale of new physics, and that's because they're the same scale. They're the 100 GeV scale. There's no mystery going on there. Okay? So this is an example of the Atlas cross-sections, and I'll just draw your eye to most of these fit very well. This WW cross-section is a little high. This WZ looks a little high at very low luminosity. ZZ, pretty close. Atlas is a little slow in updating this. So let's look at CMS a little bit more carefully. So CMS, this was updated as of HCP last year, and some of these are using literally still early data because you can do very well with gigantic cross-sections. If you've been paying attention to the EPS conference that's been going on concurrently with our workshop here, the ZZ measurements have now been updated to 20 inverse femtobarns. So these things are dead on. So ZZ is dead on, WZ is dead on, W and Z production are dead on, W gamma is a little high, Z gamma is dead on, WW plus WZ is dead on, so this is a semi-leptonic measurement. I can explain why you can't separate these two things here. The one thing that's slightly interesting is the fact that the WW measurement at 7 TV was a little high, and it grew a little higher at 8 TV. Now, okay, this is very small. This is like 1 sigma. You're saying, okay, forget about this. And we were talking about how 3 sigma things go away yesterday. We were talking about how 5 sigma things go away. But I'm going to try to convince you that there is a little bit of interesting physics going on in this channel. And there's a lot to learn about both QCD and about new physics that we can look in this particular channel, as well as Higgs physics that I alluded to yesterday, and I'm sure Elliot will talk about a lot more in his talk tomorrow. So let me do this as far as visual evidence. So CMS incorporated all these measurements in one slide. And you see that the WW measurement at 7 TeV done by both Atlas and CMS, okay, were both a little high, but they agreed quite well with each other at 7 TeV. Okay, and this is just visual. We'll go into numbers a little bit more. And then you see what happened is CMS is the only one to measure this at 8 TeV, and it moved a little bit further off the standard model prediction. Now, okay, as we talked about, I'm not trying to emphasize that this is something that should be New York Times worthy or anything like this. This is in the 1, 2 sigma areas. But it's an interesting coincidence and trend that's happening with these things, and we should look into it a little bit further. In principle, the LHC makes 8 measurements that are highly sensitive to the WW cross-section. So the standard model measurement of WW can be made at both CMS and Atlas at 7 TeV and CMS at 8 TeV, so those are the 3 measurements I just showed you. Atlas can measure this at 8 TeV as well, but Atlas has yet to put out a single measurement of WW at 8 TeV. And CMS is also stuck back to 3.5 inverse femtobarns. And in principle, this also affects the measurements of the Higgs to WW. And what I mean by it's sensitive to this is that, as I said, the way the standard model Higgs to WW is measured is by looking at a control region where you think it's mostly dominated by WW production, and then extrapolating that to the signal region where you think you're mostly dominated by Higgs. So the control regions of all 4 of these measurements are also dominated by this. And the status, of course, is that every reported measurement is higher than the standard model. Now, unfortunately, I missed Neil's talk this morning. So did Neil talk about the Fermi line? Okay. So, of course, this isn't Fermi line high, but I mean, to dig at the astrophysicists, this isn't astrophysics either. Okay. So we have some sort of an anomaly, and we'd like to press it a little bit further because it's not dark matter, and we can actually test these things a little bit better. So the WW cross-section measurements, so how well was the agreement? So Atlas and CMS both measured approximately 52, 53 picobarns at 7 TeV, and the theory cross-section prediction was around 45 to 47 picobarns using MC at NLO or using the MCFM package. Now, okay, this is, of course, ridiculous. I'm telling you this is a 1 or a 1.4 sigma effect. What on earth am I doing here? I mean, 5 sigma. If anybody of you have ever studied the recent history of particle physics, you've probably heard of something called the pentaquark, where we had some new particle that was discovered with 5 sigma, and it was discovered in multiple places. And then all of a sudden, all these things disappear. So this is, of course, ridiculous if I was just talking about this sort of effect here of an overall increase in the cross-section. But the important thing is, if you've looked at new physics measurements at Atlas and CMS, this isn't just a rate anomaly. They actually measure the differential cross-sections for these measurements as well. And for instance, if we look at the Atlas differential measurements, for instance, the PT of the leading lepton, so if I make 2 W's, both of them decay leptonically, I look at the leading lepton. I can look at both of the leptons, take their sum PT. I can look at the transverse mass of the system, taking the 2 leptons and the missing ET. Or I can take essentially the PT of the WW system by combining the 2 leptons PT and the ET miss, okay? So all of these distributions, none of them look strikingly off, but all of them seem to have some sort of behavior where it doesn't look like they're just rescaled by a constant factor, okay? That could be the case where I rescaled these things. They seem to have some shape information where in the bulk of these distributions, you actually have the excess, whereas on the tail of these distributions, they agree quite well. So we can look at these differential distributions a little bit more carefully, and we can also look at what happened at 8 TeV. That was an example of Atlas at 7 TeV. So as I said, CMS at 8 TeV, the discrepancy grew a little bit larger. Okay, it grew up to almost 2 sigma at 8 TeV. The other interesting thing is to look at some of these ratios of 7 to 8 TeV that possibly Michelangelo talked about last week. The idea is that if you really had everything under control with the cross-section, all you'd have to do is look at the ratios from going from 7 to 8 TeV, and that would just be the effects of the PDFs. So for instance, if I look at the effect of the WW cross-section at 8 TeV versus 7 TeV, and I just calculate, for instance, the change in the parton luminosity, the cross-section should have gone up by about 20%. However, if you take CMS's measurement at 8 TeV and you take it at 7 TeV, you see that the cross-section actually grew faster than the parton luminosity. And this is exactly what you'd expect if there was some new physics associated with this. Because if you go from 7 to 8 TeV and you have a slightly higher scale of a threshold for new physics, it's easier to produce things at higher energy when you have a higher energy proton beam coming in. So this is the exact sort of behavior that you would expect. Now again, I haven't put any error bars on this. The error bars are going to be similar to the error bars you've seen here because that's the information we have to extract from. But it's interesting to see these sorts of tests. And then if you combine the 8 TeV and 7 TeV measurements, now we're getting to approximately a 3 sigma effect in the WW cross-section. So if we look at the differential distributions at CMS, this is what I showed you at the very end of the lecture yesterday. And you see everything seems to look very, very good. If I look at these numbers, everything, if the data divide per prediction, it looks like it's just right around 1. There's not much of an effect here. And none of these things go off very far. But the whole point is that CMS actually measured something that was about 20% higher than the NLO cross-section. So why on earth do they describe a 2 sigma effect, have a 20% difference in the cross-section, so why aren't all these bins higher? Okay? And as I said yesterday, it's because CMS did a very naughty thing, as I'd say. In an actual standard model measurement and the differential distributions that they use, they actually put in a data-driven normalization for the thing that they were supposed to measure, okay, instead of just putting what it was supposed to be. And as I said, when you take out this data-driven normalization, you actually start seeing distributions that appear to be quite off compared to what you would have expected when you're looking at, for instance, other agreement in TT bar or ZZ or WZ. So there definitely appears to be two things going on. You have too many WW pairs being produced, okay? And you also have the effect that they have slightly different kinematics than what you would have expected. So we can go two different directions here. We can say, for instance, the standard model calculation is just wrong. Now I'm going to talk about this a lot after I talk about new physics, but there's many reasons why you actually think this is not the case. Or it could be new physics. Now, of course, there might be one other possibility. There could simply just be upward fluctuations in all these measurements. That's quite possible. We have statistical fluctuations all the time. But to me, at least personally, from smelling this after a while, I mean, everything has to pass some sort of smell test, there seems to be somewhat of a trend going on in these measurements that we'd at least like to understand. And I think the interesting thing is, as I'll show you for the rest of this lecture, that you can actually try to understand a lot about the standard model from going in this direction, and we can actually understand a lot about the possibilities of new physics by the interplay between the standard model and new physics. So the first thing we have to understand is really what it means to make a standard model measurement at the LHC. So I'm sure this was talked a little bit by Scott with the Higgs, and I'm sure Elliot will talk a lot more, and Beata later. But what it means to make a standard model measurement, it's actually quite a complicated process because, of course, when I make two W gauge bosons, they don't come out with flags and say, hi, I'm the W gauge boson, count me. We have to actually describe what we want to measure, and we have to figure out a way to take away all the stuff that's not actually the W's that we're interested in. So the cross-section for the WW, the first thing we have to do is we have to specify what are the events that we're going to count, okay? So what they did was they looked at W's, and they looked at the case where W's decay to a lepton and a neutrino, okay? So you have a lepton and a neutrino from one W and a lepton and a neutrino from another W. So essentially what they're going to do is they're going to count the number of opposite sign dileptons that they see at the LHC that come along with MET in a fiducial region of their detector. And they're going to say, hey, I'm going to count these things. Now if I want to figure out how many W's are, I have to take the number of data points that I have, and I have to take off the number of other things that give me 2 leptons and missing energy in this fiducial region of my detector. Now, of course, it's not that simple. It's not just the total number of things minus the number of background I have to do. I also have to normalize by a number of other factors. I have to normalize by my knowledge of the luminosity. Okay? So, for instance, that's what Sunil said to one of the questions yesterday when asked if there was an anomaly, if you saw more events that looked like a Z than you really thought, what would be the first thing you would do? Sunil said, I would check to make sure I really understood what the luminosity was. Okay, so that's one thing you have to do. You have to know how many collisions actually happen. The other thing is, okay, the W decays into a lepton and a neutrino. We're looking at a specific decay mode, so we have to include the branching fraction. So the branching fraction of leptons, that's pretty well under control. And there are two extra factors here, this CWW and AWW factors. So when calculating, or when they're giving us the total WW cross-section, the detector doesn't have the full coverage. It doesn't have a full 4 pi coverage. Now, Atlas and CMS are beautiful detectors that try to cover the entire detector, but there's two effects that are going on. So even if you have detected material, okay, the number of events that you predict in that from W's might not exactly match the number of events or leptons that you'd see in the detector. Okay, there can be effects that are going on as these leptons travel through. You can miss things, etc. So you have to take into account the difference between the number of events that you would simulate for W's in your detector versus the number that you actually are seeing. Okay? So this is this CWW factor. Then the next thing you have to take into account is that even if you have a very large angular coverage in your detector, you don't have this 4 pi coverage entirely. And in fact, if we're talking about leptons, you actually have a much reduced angular coverage than if, for instance, you talked about jets, which you can get a lot more for. So you have to include the effect of the geometric acceptance for what the total WW cross-section is. Okay, so that's this AWW factor here. So the actual number that's reported has a lot of physics going into it and a lot of things you have to understand. You have to understand both your prediction for your actual theory for the number of events, the background events, the acceptances and efficiencies and luminosities. Now, you also have your choice of how you want to measure this WW cross-section. So what I've drawn here is the leading order diagrams. Okay, so we have a T-channel exchange where you can produce two W's, or an S-channel exchange, or there also even is a contribution to glue goes to WW, which is formally next to leading order in QCD if I look here. So I can take these diagrams, but as probably mentioned in Jesse's talk, if I look at these diagrams, I can also start adding extra contributions. I can look at real emissions off, for instance, the quark lines. I can look at the virtual contributions to this as well. And the question is, what is the WW cross-section? Is it the total inclusive WW cross-section, or is it the WW cross-section with a specific number of jets? So what the experimentalists, what both Atlas and CMS decided to do, instead of trying to measure the total inclusive cross-section or do the exclusive cross-section with a specific number of jets, is they added a jet veto at around 25 GeV, where they said, we want to take our uncertainties from QCD and try to knock this down as much as possible. Of course, they translated it somewhere else in the end. And so there's a jet veto on this. So basically, they're just purely counting the number of events with leptons, missing energy, and no jets. Okay? So even though we love jets, and Jesse will talk more about jets, they don't want any jets in this particular measurement. Now, of course, that doesn't mean QCD doesn't matter a lot. If I look back at, for instance, this differential distribution that Atlas had, for instance, this PT of LL plus missing ET, okay? If I had a pure WW event that had two leptons, two neutrinos, okay, and I calculated the PT of these two leptons and these two neutrinos added together, what I would get is that this plot would be the most uninteresting plot out there. You would just have all of the events sitting here at 0, okay? There would be no PT for the WW system. The fact that you have PT-LL MET, okay, this comes from the fact of how the MET is actually measured, okay? It's not just based on taking these leptons and adding them together and calling that the MET. They have the calorimetry information that's going on, so you have actual energy depositions from all the radiation. They've just demanded that once you cluster these into jets, that you have no jets that are above a certain PT threshold. But all of this effect is coming from soft gluons that you're radiating, and that's giving you this recoil of the WW system. So this essentially is measuring the QCD recoil that's going on. Okay? Yep.
So what is the theory then in this specific example? Is it a jet veto with some cross-section, or is it really just NLO?
So this is NLO plus parton shower, and I'll show you an example of resummations for this as well. Okay. But yeah, you have to be careful about what goes on here. So the basic measurement, as I said, is you're counting two opposite signed leptons, missing energy, and a jet veto. So if we were looking for a BSM explanation, we just need sort of these basic ingredients, okay? So we need a final state of a BSM system that has opposite sign leptons and missing ET with nothing else, essentially. So for instance, if you had gluinos being produced that then cascaded down to electroweak particles that gave you Ws, and these gluinos came along with extra jets, that wouldn't help you at all, because these events would be vetoed because of the jet veto. So you have to be careful about this bit. So you just want this final state, essentially. Now, of course, this doesn't imply that there have to be real W's anywhere in the system whatsoever, okay? If I had some other thing that made two leptons of opposite sign, this could give me the same signature. Of course, it doesn't hurt if there are real W's either. I'm going to give two different examples of this, and it's interesting to compare and contrast them. So an example of a favorite tool experimentalists have, and they actually use this in WW measurements to bound these things, is when you talk about standard model gauge bosons, the first thing experimentalists set bounds on are triple gauge boson couplings, okay? So the idea is we know the standard model interaction of these three gauge bosons, and the idea basically is that there is some new physics that we've integrated out here to create a shift in the triple gauge boson coupling. Now, of course, when you have new physics that's at a higher scale and you integrate this out, what you're going to expect to see here is that you're going to expect that this is going to matter more and more at high energy. So what happens if you have a deviation from a triple gauge boson coupling shift, you're typically affecting the tails of all the distributions. However, the problem that we saw with these differential distributions was the tails matched quite well. It was the bulk of the distributions that didn't quite match as well. So these are not the best solution to trying to explain these things. So we need two leptons, missing energy, not much else because of the jet veto. We like kinematics similar to WW. We need a cross-section of order a few picobarns to make a difference, because that was the order of the cross-sections. They measured 60 and the prediction was 50, or 50 and 40 for 7 TV. So this is done by the same thing we just talked about yesterday. Electroweak production of gauginos is a particular example. So I'm going to focus on electroweak gauginos in the context of supersymmetry. I'll also give another example here later where we talk about SLEPTON production, because this can create leptons but not actually having any W's. Now, the basic thing I'll start with is the idea that I know Natalia gave a couple lectures on supersymmetry last week, but the basic idea is that we have neutralinos and charginos in supersymmetry, and they're controlled essentially by three different quantities in supersymmetry breaking. There's the M2 contribution, which sets the Wino mass, so it sets these guys' mass. There's the M1 contribution that sets the Bino mass, and then there's the mu contribution, which sets the Higgsino mass. Now, of course, depending on the size of all these three different soft parameters, M1, M2, and mu, these things can become highly mixed with each other. But for the 0th order thing, I'll just give you an example where we're going to treat these essentially as gauge eigenstates, where we can have a Wino contribution, a Bino contribution, or a Higgsino contribution. So if I look at a given topology that I produce a charged state, for instance, chargino pair production, charginos can decay to the lightest neutralino and emit a W. So we talked about this and bounds on this yesterday. Now, emphasizing the same point that I made yesterday, this doesn't have to have anything to do with supersymmetry. Supersymmetry is just a signal generator for my purposes right now as I talk. If you wanted to have your favorite model with a heavy lepton that decayed to a heavy neutrino by the emission of a W gauge boson, feel free, go at it. For instance, if you look at many of Pospelow's models, he loves to do these kinds of things for anomalies. It doesn't matter. The basic idea is a topology, though, where I emit a W and have some missing energy particle, and we want to see what the ramifications are. So an example of this would be if I had a gravity-mediated spectrum where I just stuck the Wino mass at order 100 GeV right at the left limit, and I stuck the Bino mass at order of GeV. Now, I'm not going to talk about the implications of dark matter. There's an interesting case for that later on, where you can actually account for dark matter as well. But this is just a quick simplified model where I stick the Winos at 100 GeV and the Bino down at order of GeV. Now, if I do this kind of thing, and if I generate all the topologies, the beauty is if you start playing with electroweak new physics and you start giving electroweak quantum numbers, you know not only what you have for what you want, but also what comes along with it because of the symmetry. So this is the process that we want. We want Chargino pair production that gives us 2 W-gauge bosons and 2 neutralinos, the missing energy. However, unfortunately, because I said let's stick in a WENO, I also immediately have a diagram which is the analog of the WWZ vertex if I just switch it from using it this way to using it this way. So including pair production of Charginos, I also have the associated production of Chargino and neutralino. So this is a partner of the Z sitting here. The unfortunate thing is every time I produce this, I'm also going to be producing this, which gives me a WZ final state plus missing energy. Now that would have been great if both the WW cross-section and the WZ cross-section were both measured to be high, but the WZ cross-section appears to be quite right as far as we can tell. And this was also gone if we looked at the bounds from yesterday's lecture. So for instance, if you look at WZ production plus missing energy, you see that the bounds extend, when I look at the trilepton signature, well into the 200 to 250 GeV, looking at this measurement using just 5 inverse femtobarns. So if I'm talking about the range of 100 for the Charginos and 0 for the BINO, we're definitely excluded from the WZ measurement. Okay? So you could say, well, I know what electroweak symmetry is. Instead of using WZ here, I could have said, let me mix up the neutralinos, and instead of having this thing decay mostly through a Z to a BINO, I can mix it in with some Higgsino component, and I could have had this thing decaying through a Higgs to a neutralino. Okay? Well, unfortunately, as we showed, and I mentioned yesterday, the WH final state is also ruled out by an ATLAS measurement. It's not an ATLAS measurement that they actually used a supersymmetry group to do. But if you look at the Higgs measurement, where they look for associated Higgs production at 7 TeV, where this Higgs went to BB bar, we would contribute events to this search, and you can rule out Higgsinos up to about 160 GeV. Now, take this with a grain of salt, because it looks like, as I said yesterday, this was a downward fluctuation, so possibly this thing is still alive with more data. But unfortunately, this also comes back to where we need experimentalists to do a little bit more of the work. Because if you look at Higgs results, I'm sure Elliot will tell you about these for WW, but in some of the other harder to see cases, also for instance, when we talk about substructure measurements that Jesse will talk about, or just even a little bit more background dominated channels, what happens is that these measurements stop being these kind of simple counting experiments where I said number of data events minus number of background events divided by some acceptance and efficiency. They become boosted decision trees where unless the experimentalists give us more information, we can't go any further. So this is the current bound, and until Sunil gives the final number that he was promising yesterday, we're not going to get any further than this right now. But it's an interesting effect. So basically, though, if you want to construct a model here, you want to have WWs but not WZs or WHs. Now, as I said, any good theorist can play around with this, and you can try to come up with other regimes where you can get WW production, but not WZ production or W Higgs. I mean, as we talked about at the discussion section, I mean, you can play with any kinds of models that you want and basically make things that work. So an example of these things, I'm not saying this is the way the universe works, of course, an example of these things is instead of thinking of the gravity-mediated picture of supersymmetry breaking, if you think of the gauge-mediated picture of supersymmetry breaking, what happens is at the bottom of these cascades, you can have gravitinos sitting instead of some neutralino coming from one of the gauge eigenstates of or one of the mass eigenstates of the neutralinos. So I can look at gauge mediation, and what happens is once you get to the lightest supersymmetric particle, you then decay to the gravitino. And in the case of you having a Chargino NLSP, I won't go into this in any detail. If you want to talk to somebody about this more, I think I saw Graham Cribbs here earlier, and he wrote a paper on Charginos NLSPs before, so you can bug him if you see him. But if you go to a specific regime of mixing between these WENO and Higgsino gauge eigenstates, then you can create a situation where all of the Charginos will then decay to a W in gravitino, but the neutralino will also first decay to the Chargino because it'll be heavier than the Chargino, and then the Chargino will decay then to the W. So these events will give you WW events. These events will also give you WW events, but they'll also give you this extra W star. But these things will have very similar kinematics because they're just split by a little bit, similar masses. So this W star will be incredibly soft, so you won't see this in the detector. So these things will both look like WW events. So if we take the kinematics right around the LEP limit, where we put the charginos at around 110 GeV or so, the cross-section that you get for the supersymmetric contribution to WW is about, well, from these two processes, along with the chi2 zero, you get about 4.3 picobarns, which is exactly the sort of effect that you were looking for. We were looking for a 5 to 10 picobarn bump. The question, of course, is I can get this 5 to 10 picobarn bump pretty easily. I could have done this with the triple gauge boson couplings. The question is, what does this manifest itself in differential distributions? The remarkable thing, which we really did not try to do whatsoever, was that all of the places where you were off in the data, that's exactly where all the events fill in. So what these plots represent, the beige contribution, or this yellow contribution, is the standard model contribution. Okay? The little orange contribution here is the effect of the Higgs, which at this time Atlas had not signed on to saying this was the particular mass of the Higgs yet, so they didn't put the Higgs contribution in. So we put that in. And the red contribution is the effect of these new charginos. So for instance, if you look at the tails of these distributions, the tails still fit beautifully. Whereas the bulks of the distributions, where you had problems before, get filled in preferentially. And if you do this on a statistical way, instead of just showing you this as a plot, it's actually remarkable. If you take the chi-squared of all the differential distributions given by Atlas or CMS, you can actually show, if you include the effects of the charginos, the chi-squared is actually cut in half compared to the standard model. So this is the only process I know of at the LHC where the new physics idea actually fits the data much better than the standard model itself. Now, of course, that doesn't mean that any of this is right, but it's an amusing thing because I don't have any other example I can just say, hey, in this model I can fit this better or something like this. We can always come up with models that aren't ruled out, okay? But when you actually fit better than the standard model, it's an amusing thing. If you do this at ATV with CMS, it also preferentially fills in the parts of the distributions where you're not doing very well. And as I said, CMS was actually quite off at 8TV once you took out their data-driven normalization. In fact, the p-value for the standard model alone in the CMS measurement is 0.001. Okay, that's a very crappy p-value for the standard model. If you include the standard model plus the Higgs, as I said they hadn't included it, it jumps up by quite a bit. Okay, the p-value improves by a lot if you include the Higgs, but it's not nearly this contribution that these charginos are given, which is the red. The orange is the contribution from the Higgs. If you include the standard model plus charginos not including the Higgs, it jumps up to 0.3, so the charginos have a bigger effect than the Higgs alone. And if you include the standard model plus the Higgs plus the charginos, you start getting a p-value that looks very nice for this WW measurement with CMS at ATV. Now you see that these distributions, so all these lines here, I didn't explain what these lines were, but these are the basic contributions from the various different new physics processes. For instance, chargino pair production, chargino neutralino, etc. And you see that they have these different shapes compared to what the standard model backgrounds or what the WW measurement actually looks like. They actually naturally fill in certain regimes. They like to fill in down here compared to having quite as much of a tail. Of course, approximating this using the same way that Atlas and CMS did with the parton shower. So it's an amusing effect that you can get that these things fit a lot better than actually the standard model itself. So what are constraints on this scenario? Well, an amusing constraint, and which also Sunil mentioned because that's why we contacted CMS about this, is the fact that if you do this particular model where you have a chargino NLSP, this neutral state has a choice to decay to a W plus here and a W minus here, or vice versa. Okay, it can go either way. So these two W's coming from this particular production mechanism can have either same sign W's or opposite sign W's that come out of this. So one prediction, if this is true for the new physics, is that there should be some contribution to same sign dileptons that come out of these physics models. And so that's one of the constraints that you can put on these. And as well, in principle, the opposite sign dileptons that we're getting out of this, as you see here, the shapes fill in the bins that we like with the WW distributions, but they do have different kinematics than WW itself. So if you look for shape tests a little bit more sensitively, you could look for these things. So the kind of summary on this particular scenario is that opposite sign dileptons don't touch this scenario at all. Same sign dileptons with the most recent measurements from CMS with 9 inverse femtobarns says that this is going to be either ruled out or not using the full data set. So we're on the edge here. Now, the other amusing thing is, this is an example for all of you. If you can talk to experimentalists and try to understand the interplay between these two different things, you can also motivate experimentalists to do new searches. So this is exactly what we did with Atlas's SUSY group, where we said, hey, look, we can do all these interesting things with WW. Can you actually see this in WW? So this opposite sign dilepton measurement I'm talking about, this is a measurement that was made beforehand by CMS, but Atlas actually went out and searched for this particular topology of a Chargino pair production followed by a W neutralino decay. And what Atlas actually, they tried their best, but they're not actually able to exclude this scenario. They can only bound the cross-section at a factor of about 2 to 3 times what actually supersymmetry would say the cross-section is. So this is an amusing thing, where if you can motivate the experimentalists, they'll go out and look for this. That's not to say necessarily you take your favorite model and they'll go do this, but if you put in the work and talk to experimentalists and go back and forth, you can actually get experimentalists to try to make new measurements. So there's other interesting effects that can come from Chargino productions. Now, one interesting thing that we'll jump into the stuff I talked about Higgs to WW at the end of yesterday. This particular type of new physics will not affect Higgs to WW sensitivity. The reason for this is that if you affect the control regions and the signal regions similarly, you're just going to rescale the whole thing. And the way that Atlas makes projections for their sensitivity is based on after you've rescaled the control region. Okay? They don't say this is just based on what the NLO calculation or NNLO or N cubed LO calculation tells you what the rate should be. It's after you've rescaled the control region. So if you affect the control region and signal region similarly, you're going to not affect the actual sensitivity. Now, there are ideas put forth by, for instance, Dieter Zeppenfeld and all, of other models that affect the sensitivity. Lots of these things can be rolled out basically immediately at kind of the 9-10 sigma level. But if you do have to upscale your control regions at all, you will see a manifestation of this because of this upscaling. Amusingly, you can also affect Higgs to gamma-gamma rates, as I said. Whenever you have new electroweak particles that couple to the Higgs, these things run in loops, and you can affect the Higgs to gamma-gamma rate. Of course, this is still well within kind of the errors of what we're talking about, and especially after CMS has drastically dropped down their signal strength for Higgs to gamma-gamma. We don't care about these things quite as much as we used to. And as I said, same sign dileptons or other new physics could be interesting for this in the future. So there's another example by Robielecki et al., where they said, well, instead of using direct electroweak production for Charginos, what if we had supersymmetry still being relatively natural? Okay? So if I produce stops at a low scale, and the stops decay into a B Chargino, and then the Charginos decay to a W neutralino, this will look like WW production. The only thing I have to do is I have to get rid of these B jets for it to actually show up in the WW measurement. So if you squeeze the stop and the Chargino masses close to one another, you squeeze out the energy that can go into these B jets, and all of a sudden you have stop production looking identical to WW production, which is an amusing effect. So what they did is they looked at kinematics where you've squeezed out these B's, and what this plot shows is this is the chi-squared of their distribution, so blue is the best fit, is that you actually can get quite good fits in this region here in the stop parameter space. Now you can say, hey, didn't Atlas and CMS already search for direct stop production? So this is this black hashed line here. So the region below this is excluded by the Atlas direct stop search. But you see this region here. If I have a stop in the 200 GeV region and a neutralino in this kind of 100 GeV region, you can still fit quite nicely, and you can look at this with differential distributions as well. So they chose our same color scheme and figures for plots. But you see here that these also can kind of fill in these bends that are off by a little bit. So this is very interesting from the perspective of if you would like still to believe that supersymmetry can be natural, here's an example where not only the stop can be 200 GeV, it can actually improve the WW measurement too. Okay? Now this still, of course, does not explain at all how the Higgs is 125 GeV, but of course when you're talking about light stops, you've already said we're ignoring that question and separating it. But it's a very interesting kind of parameter set that you can go into and see what could be going on. Now, of course, no one said there had to be real W bosons anywhere at all in this process. That's the beauty of whenever you look at an experimental measurement. Now, they're trying to match this back to a particular standard model process. They're trying to match it under a new physics process. But the only thing you see are these basic objects of leptons, jets, photons. You don't know where they actually came from. So here's an example of a topology where I pair produce leptons, which then decay to leptons and neutralinos. Okay? So this thing would count as the exact same final state from the perspective of any experimentalist trying to measure standard model WW. Now there's two problems with this that you'd say naively happen, which is the fact that leptons, since they're scalar particles, are going to have a smaller cross section than these partners of the W's, because these things are charginos and fermions. It'll also naively possibly have a little bit harder missing ET spectrum, and we said we didn't really want to affect the tails. And this comes from the fact that all your missing ET here is coming from neutralinos, coming from these two-body decays, whereas in the case of chargino pair production, you made W neutralino, so you got basically four-body contributing to the missing energy from the two neutrinos plus the two neutralinos. So this could be a problem, and luckily my student who's here, Pinru Tien, he looked into this a little bit more carefully and showed that this wasn't actually the case, that it really messed up the tails of the distributions. In fact, it turns out that it fits just as well as the charginos or the stop examples. If you have, for instance, the left-handed and right-handed stops sitting right at the electroweak scale, about 100 GeV. Now, instead of having the bottom of the spectrum sitting about massless, if you bring the bottom of the spectrum up to about 60 GeV, then the leptons seem to fit the distributions just as well. It preferentially fills in the bins that don't work as well, and here's the same plot for the charginos. Okay? It has the same sort of effect of ameliorating the difficulties you had in the WW cross-section. So it's very amusing that you can fit this just as well using a non-WW final state. It's an example for new physics that you should always keep in mind, that even if you're trying to explain something that the experimentalists have measured using some particular final state, you can get to that final state in many different ways. Okay? Now, you can also do this for any of those who are thinking about supersymmetry model building. It's typically not very attractive to have both left-hand and right-hand leptons sitting at the same spot. Gauge couplings tend to bring masses up, so left-handed things tend to be heavier than right-handed. Now, I can't give you an example that gives you just right-handed ones being sufficient to contribute. They just don't have a large enough cross-section. But you can get just as well of a fit if you just do this with left-handed leptons. So you can do a little bit of model building to separate left-handed from right-handed and get the mass spectrum. But that's just an aside. Now, this would be interesting if it was just the WW case. As I said, this is the only measurement I can give you where I can actually fit better than the standard model. But the beautiful thing about electroweak final states or electroweak pair production of any new particle or electroweak production of new particles is that they can have lots of influences elsewhere. Okay? Now, a TeV gluino, that's great. It matters a lot, of course, to the running of the stop mass and influences there. But other than that, it's just generating a signal for jets plus missing energy. Heavy gluino doesn't really do anything for me or talk to me about anything going on in the electroweak sector other than it's through its effective running. So you can first question whether or not anything dangerous can go on and what are its effects that it could show up elsewhere in. So unlike the chargino case I gave you, there aren't any dangerous processes for leptons. Just like the stop case, there weren't any problems with same-sign dileptons, for instance. And similarly, if I produce leptons, I'm not going to get any trilepton signature that I'm worried about, and the same-sign dilepton signature is gone. And the only effect I could see possibly with these left-handed neutrinos sitting around here is that I can produce things that look like a single lepton plus missing energy. But then my background is W production, and if you remember this logarithmic scale, W production is so gigantic you're never going to see any effect of this in terms of the background. Now, but as I said, electroweak states can be good for many things, okay? We believe dark matter, the whole idea of the WIMP miracle is that it has kind of weak scale interactions and weak scale processes going on. So there is a long history of looking at different kind of gauge eigenstates to be dark matter. And it would have been great if the dark matter was some sort of mix of all the neutralinos, and as Nima said in the discussion section yesterday, but that seems to be dead on arrival. But there is an example if we look at, for instance, Beano dark matter. Now, Beano dark matter needs a little bit of help because if you remember, basically the formula for the dark matter relic density, we don't want to have too small of a cross section. If we have too small of a cross section, the thing doesn't annihilate early enough in the early universe, and we have too much of it left over. So we need some mechanism to get rid of this overabundance of dark matter. But it's been well known that a Beano can be the right relic thermal dark matter as long as you had light SLEPTON sticking around as well. If you have a light SLEPTON sticking around, you can have this T-channel annihilation to leptons, and you can get the right relic density. So this is a very amusing fact, and these light SLEPTONs, even though we didn't engineer it, we were just concerned about the WW measurement, actually can give you the right relic density without any work. Now, direct detection, as I mentioned in the discussion section yesterday, you also have to worry about bounds for weak scale dark matter if you think about direct detection. If you have direct detection that's mediated with a Z, you're almost dead pretty much in any model because the rate just is too high. However, if you have a dark matter particle that basically only interacts with your target through Higgs interactions, then you're actually okay with all the xenon 100 bounds as well. And so in this case, your direct detection sails right through. And of course, if you have dark matter interacting through only, as people call it, a Higgs portal or a Higgs interaction, this is exactly right in the range that Lux and xenon 1 ton will be able to probe in the next few years. So it's very interesting from the perspective of dark matter. So that's why we started with a simple idea that we were trying to come up with something for WW, and you find all these other consequences. Like you can get a very, very good dark matter candidate that has experimental signatures coming up very soon. There's other interesting things that go on with light SLEPTONs. So for instance, for some of you that are way too young to know about this, there's been a long-standing anomaly in the G-2 of the muon, okay? So it's off almost by 3 sigma from the standard model prediction. And in fact, this is such a famous anomaly that Kirill Melnikov and Arkady Weinstein actually wrote an entire book on this process. I'll plug this because it's a very beautiful book, and it incorporates a lot of different physics that go on to this, and everything from large N QCD onto form factors and everything else. So it's a very cute book. But there's been this long-standing 3 sigma discrepancy. Now, of course, if I look at a diagram that contributes to G-2, what do I need? I need new physics around the electroweak scale to create this big discrepancy, and a muon coupling to a light muon and a neutralino, and the muon radiates. This is exactly the process that gives you a shift in G-2. And again, we weren't trying to fool with the numbers to kind of just get this alone, but everything sat in the right ballpark to explain both WW dark matter and this G-2. In principle, you could also affect Higgs to gamma-gamma using STAUs, okay? I won't go into this in too much detail because I don't think anybody really cares about Higgs to gamma-gamma that much any longer, but you have to do some mixing games with the STAU sector. But in principle, you can generate spectrums that would give you the right contribution. So 3 out of 4 anomalies. So I can get the WW, I can get dark matter if you call that an anomaly, and I can get G-2 as well. And Higgs gamma-gamma goes away, so let's call it 3 out of 3 anomalies. That's pretty nice. Now, this is a schematic view of this in terms of the neutralino parameter, neutralino mass versus SLEPTON mass. So I draw this to kind of focus you on the details. So this red area here is where the right dark matter relic abundance comes in, okay? Here is where you sit on the Higgs pole, so you get rid of all the dark matter very fast. This blue area here is where you get the right G-2, and these contours here are various preferences for fitting the WW measurement the best. So all of these things seem to overlap in this region, as I said, where I'm talking about the Electroweak scale, and this is about 60 GeV. Now, I showed you in this region because I can now show you the plot that we actually have in the paper, and it's much uglier than that because you have all these contours overlapping. But it basically is the same qualitative features. We have dark matter, relic density being correct. We have the WW measurements being correct, and these reds are the G-2. So amusingly, you can get all of this physics coming from the exact same place, and it'll be very interesting to see how this goes out in the future. So there's 3 different examples of new physics that can contribute to this, and we'd like to understand if any of these are correct. Now, of course, you have to take the flip side of this, and you have to say, well, this is completely ridiculous. I mean, you're not ruled out on any of these possibilities, but if you're telling me that there's 100 GeV Electroweak states sitting there this entire time, and you can solve all these anomalies, I mean, come on, give me a break. It's got to be up with the TeV scale, or there's no new physics, no discrepancies anywhere else. So then you might want to look at standard model possibilities or experimental possibilities. Could this just be an effect that wasn't calculated correctly, or something experimentalists didn't take into account well? So there's a number of different possibilities, and it basically comes back to that starting formula that we have of that the cross-section you actually measure depends on the number of data events minus the number of background events divided by acceptance, efficiency, branching fraction, and luminosity. So we can essentially look at this formula and try to isolate what are each of these components. Where could have something gone wrong? So the first place we can look at is, could something have gone wrong in our background estimates? Obviously, they don't have 100% purity. These aren't all WW events. There's lots of things that make WW in the standard model effectively. Like, for instance, TT bar production is one thing that makes Ws all the time. So we would like to understand whether the backgrounds could be wrong. So let's look at the actual number of events that Atlas saw. So in data, Atlas saw about 1,300 events. The WW contribution that they thought from their signal was about 824 events. Okay? And the various leading backgrounds are coming from top pair production, W plus jets, where one of the jets would fake a lepton, Drell-Yan production, other dibosons like WZ, and you miss one of the leptons. And you see that these things contribute about 370 events to give you a total expected of about 1,200 events. Now, if I look at this, I need to account for 100-some events, okay, between these backgrounds and WW or any new physics. Now, the thing you notice is that this is a very good signal purity, okay? When we talk about like discoveries at the LHC, we're always talking about kind of like an S over root B of order 5 or so to see something. They really nailed the WW. This thing has like an S over root B of like 37 or something, okay? You're really seeing W's. If you want to account for this many events being off, you really need to shift any of these backgrounds by quite a bit. Like you have to say, oh, magically our top cross section, we were just off by like, let's say a factor of 2 in the top cross section. You're not off by that much in any of these backgrounds. So you have to really, really be wrong on the backgrounds. So my contention is that this is probably not where the meat of the problem is. Okay? You have to be really off in the backgrounds. And you don't get to just use one cross-section for one process and a different in everything else that you're using in all the other measurements. There could be just a problem with the WW cross-section. Maybe the W cross-section is increased compared to what it should be. Now, the K factors from going to leading order to next to leading order in WW are about 1.6 to 1.7-ish, which is a sizable K factor. But when you look into other K factors and understand what next to leading order estimates would give you, you really need a 20% effect at next to leading order. And already, actually, there have been some calculations that have estimated some of the leading pieces at next to leading order. And this is talking about a few percent effect, not a 20% effect that we're trying to get here. There's other amusing effects with the WW cross-section. As I said, Atlas and CMS, neither of them included the Higgs in the actual measurement because they hadn't satisfied themselves that it was a Higgs at 125 when we put it into the measurement. So what we did is we put the Higgs in. When I look at these plots, it's this little orange thing sitting here is the Higgs. The only thing that we're able to do, though, is we can just take the Higgs cross-section and put it in and add it to this. Well, actually, Campbell, Ellis, and Williams, when they did the calculation at next to leading order with the inclusion of the Higgs, actually shows that the Higgs interferes destructively with the standard model contribution of WW. So instead of actually increasing the number of events you should see, it should actually reduce it. But of course, the Higgs was a small effect in the first place. The NLO, full NLO electroweak, not just the leading corrections, were computed last summer for the very first time. These also reduce the cross-section by order 3–4% or so. So they also go in the wrong direction. So these things, none of them are going in the right direction or are a big enough effect. And one last place you could look at is, okay, is there any kind of systematics that we need to understand of what's going on? So the leading systematic uncertainties, and this also is the statement of, hey, can we also show that this truly is an anomaly? Because as I said, these were all 1, 2 sigmas. You can buy it to 3 sigma. If you knock down, or if the experimentalists knock down what the systematics are, all of a sudden you have something that was a 2, 3 sigma effect going into a 4, 5 sigma effect. So we'd like to understand where the biggest source of systematics come from. So there's 2 different sets of systematics. One for the acceptance on this AWW quantity, which I said was the extrapolation from the fiducial region to the entire detector, and one essentially having to do with the efficiency of how well you simulate these objects in your detector. The biggest source of uncertainty for both of these comes from the so-called jet veto that I talked about. So the idea was we didn't want to have to deal with all this extra QCD radiation going on, so we wanted to set a jet veto that was relatively low on these processors. The experimentalists wanted to set a jet veto that was relatively low. The problem is, how do you actually estimate the uncertainty with this effect of a new jet veto? And this actually is a bit of a tricky game. Formally, what you would like to do is you would like to calculate the process of WW with an additional hard radiation. So we'd like to calculate a diagram like this with an additional gluon. But we'd like to calculate this at the next order beyond this. So this is like calculating next to leading order WW. The current state of the art is next to leading order WW, although Kuhn recently just put out some of the master integrals for these 2 loop effects, so maybe this will be something that we'll see in the near future. But right now, the jet veto is the largest source of uncertainty, and right now what the experimentalists do is instead of, since they don't have this calculation, they have to do this in a data-driven way. So you'll hear this over and over from the experimentalists, data-driven physics, data-driven physics. The way they do this is that they take the Monte Carlo estimate for how often a jet should fail this veto, and what they do is they look in a region where they think they understand what's going on. So, for instance, they look at the window where these 2 opposite sign dileptons would actually give you a Z. Okay, so E plus E minus or mu plus mu minus in the Z window. Then they take the number of events they see in the data that pass this jet veto, compare it to what the Monte Carlo should have told you for the Z window, and normalize this Monte Carlo prediction to get what they actually use in their data for what they say, what is the actual probability that we fail this jet veto. Now, there's a number of problems here because this is measured at the scale mz, whereas this thing is dominated by 2mw, the threshold for production of 2mw. So there's an uncertainty of how you extrapolate this scale up to this scale, which correlates this large uncertainty that's going on here. Now, you could say, well, maybe I just don't know the physics. Maybe there's some extra logs coming that I haven't done with the right jet veto uncertainty. There's a lot of QCD theory that's just based on this in the last 2 years, okay? So there's a lot of people working. As I said, all of these things can touch on many different types of physics. However, even if this uncertainty was reduced, if the calculations improve, this is not what QCD wants to do, though. What you have to have is you have more events than you expect. So you have to have your distributions essentially causing more things to pass the jet veto than fail it. So you have to have QCD shifting your whole distribution to be soft. But as I'll show in a couple of slides, if you look at resummation of these things, QCD wants to actually push these distributions out. And the reason for that is if I don't have a big jump in the overall cross-section, like as Jesse was alluding to in certain things, like you'd expect things to like blow up at low energy. How does this come out with a finite thing in the end of the day? Well, if you match this onto the calculation where you say you don't jump the whole cross-section by a lot, and QCD is regulating these soft virtual emissions, okay, what happens is that the tail gets pushed out. Things tend to look harder when you do these sorts of calculations, and I'll show you an example of this quickly. The last thing you could say is, even if any of these possibly are not the right answer for this, or I'm just giving you a slightly incorrect version of any of these things, is QCD is beautiful because QCD is so darn universal in many instances, okay? Just like we would love to come up with some way to enhance CF over CA, that's great, but we don't have another handle. It's just CFs and CAs that enter into these basic underlying things. Similarly, if you do higher order QCD corrections to any electroweak process, they don't care, okay? The hard process is the same. If it's a colorless final state, you only care about the initial state. QCD just plays with that. So, for instance, if I was having something that shifted the WW by 20% and shifted the kinematics of this, it should have affected ZZ. It should have affected WZ. We should have seen something here, whereas everything seems to agree very well. Now, this is just a little bugaboo I have about the way experimental things are measured. And you should always make sure, whenever you see a measurement, make sure to ask how the things are done in terms of what is the theory actually that goes into this. Because experimentalists sometimes have this funny thing of when something doesn't fit too well, they switch Monte Carlos. But they use one Monte Carlo for a process that should, from all intents and purposes, give you the same answer for two different things, but they'll use two different Monte Carlos because they fit better in one case or another, but QCD says these two things should fit in the exact same way. So you always have to keep people honest from the theory side of this. So even if any of these things were true, you still have to ask yourself, why on earth does this agree? So what's the state of the art for these cross-section calculations? So the WW of cross-section, as I said, is known at NLO plus a parton shower. And the question is, what's the variation on this? So apparently there's a good amount since, for instance, the Monte Carlos have been switched back and forth. And an example of this, Bob Hold'em looked at, because this is a very interesting channel. WW matters not only for Higgs, but it matters for WW itself. And so Bob Hold'em looked at this at the end of last year and said, well, what happens if I start varying between Herwig and MC at NLO? And you see that there can be a good amount of variation between the actual NLO Monte Carlos, okay? And this has implications for Higgs searches. But the amusing thing is that Atlas and CMS got the same cross-section at 7 TeV, and CMS still uses MagGraph for all their shapes. They don't use an NLO generator for their shapes. So there's a little bit of a problem here that's going on. And we'd like to have some more reliable theory systematic estimate for these cross-sections and jet vetoes. So the two basic things where a lot of work can be done and has been done in recent months and years is looking at the NLO cross-section and looking at various resummations of this process. So we'd really like to understand how we take QCD and directly apply it to all these various things. And QCD, I like to think of this masterpiece. And the question is, this masterpiece, which is made of all these different tools that we're using. For instance, we have Monte Carlos. You see, you have like Pythia, Herwig, MC at NLO, various things. You have effective field theory techniques, for instance, with SCET. You have resummation techniques like Collins, Soper, Sturman, and others. And then you have people who actually calculate the hard matrix elements at very much higher orders. And the question is when you combine all these things, is this masterpiece you have here made out of individual masterpieces, or is your masterpiece made out of a bunch of old magazine covers that nobody wants and nobody reads? So I'm going to first talk about resummation briefly and figure out how can this be applied in the most recent, most useful way, and what's the state of the art. So there's various types of resummation, and I think maybe Jesse will talk about this a little bit with jets, or maybe not, but the basic idea is there's different types of logs that you can resum when you do these processes. And for instance, you can resum in QT of the actual WW system. As I said, this PT of the LL plus MET, this is all due to these soft gluon effects. Okay? This plot would just be a delta function at 0 if it wasn't from the effect of QCD. And you have to sum up all of these soft gluons to actually get this distribution. So the QT resummation for the WW process was calculated by Grazzini in 2005, and it's an amusing effect. You see that what happens if you compare the MC at NLO effect, which is this red dashed line, okay, compared to the next to leading log that he calculated in this paper, you see that at high QT of the system, the resum calculation actually makes the spectrum harder, as I said. And this comes from the effect that QT resummation, you match it onto an NLO calculation, so you get the same cross-section. So by definition, it's just moving the shape around. And you see this even more better illustrated here by calculating the actual ratios of, for instance, next to leading log compared to next to leading log. And you see that the spectrum just becomes harder as you go to higher PTs. So this calculation has been done. This isn't exactly what the experimentalists match onto, though, because this calculation was done fully inclusive in rapidity. And as I said, you have to worry about all these effects of how you take the acceptance and the actual cuts of the detector into account. So we're looking into this of how we make this better differential distribution. But the basic lesson is that the QT resummation tends to make the QT spectrum harder than the NLO effect. In this plot, this background is calculated with MC at NLO. Okay, this is the NLO effect. And you see what happens if I look at the QT of the system. At harder QTs, I agree very well. It's all the problem is this low QT region. Okay? So by doing the QT resummation, it doesn't help me. It actually increases the discrepancy with what the experimentalists find. You can also look at threshold resummation, and this calculation was just very recently finished by Sally Dawson et al. Just a couple weeks ago. And this effect includes also some of the leading next to leading order pieces, and they showed that this was actually a tiny effect. This is order 0.5% to 3%. So the kind of these leading next order effects are a very small effect. So even though QCD could have some effect on these measurements, and there's lots of different QCD types of theory that go into this, all of this is a small effect or it goes in the wrong direction. So, and bottom line, it would have affected ZZ as well. So the real question you have to understand is why on earth does this agree? And you don't just get to play with one channel with respect to QCD. You have to understand the universal effects of this. So one last thing is, of course, all of these things could have just been a ridiculous accident in terms of we have all these fluctuations that we're all treading in the same direction. Every time a new WW or Electroweak measurement has come out in the last year, I'm always ready to drop this instantly and say, okay, this is done. But the problem was every single one kept going in the same direction, so we just kept looking into this and seeing what could come out of this. So the question is, do you only care about standard model measurements for anomalies? And the answer to this, of course, is no. Even if you're not trying to chase down an anomaly, you still should look at these standard model measurements and see what it can actually imply for new physics. So, for instance, this is what ATLAS actually can set bounds on. So ATLAS, as I said, loves to bound shifts in the anomalous triple gauge boson coupling. And as you see, if this delta kz and these lambda parameters are things parameterizing how much I have shifts in these triple gauge boson couplings. And you see what happens, the standard model WW measurement that they made, if I include these shifts in the triple gauge boson couplings, actually shift the tails, as I said, and they can set bounds on these things because they're affecting the tails of distributions. Well, you could also say, well, what happens if I just had some new Electroweak physics that was sitting here? Okay? As I said, ATLAS hasn't actually bounded this region itself so far, or CMS as well. So what we did was said, let's reverse this whole procedure. Instead of trying to explain the anomaly, let's just scan and understand what the possibilities for new physics are. So what this plot shows is that this is the LEP limit sitting here at 100 GeV. Okay, so that's kind of an inviolable limit because whatever you screw around with the final state, it's really hard to get around LEP. LEP is just a E plus E minus machine and you're done. This regime here represents a direct search for SLEPTONs that CMS did with 9 inverse femtobarns. And you see CMS here was actually able to exclude a lot of direct SLEPTON production. They were actually able to go beyond LEP for the very first time ever. But you notice that there's this intermediate white region here. And this comes from the very nature of kind of the data-driven search techniques that are used at the LHC right now. You have to have a good control region, and then you extrapolate in your signal region to say what's going on. The problem is you always have this funnel between LEP and what the LHC is, because as you get into this funnel region, your kinematics become more and more WW-like. And this sort of thing holds for WZ, ZZ, any electroweak state. If you're trying to separate LEP and the LHC, there's normally a hole that you'd like to try to fill because you'd like to try to understand standard model kinematics. So what we did is we said, if I have a simplified model where I have a left-hand and a right-hand SLEPTON decaying, okay, and this is the mass parameter space, you can actually use these WW measurements from Atlas and CMS to actually exclude and fill in these funnel regions here. So even though these things were never thought to be purposed for this sort of thing, you can actually repurpose standard model measurements and fill in things that the experiments haven't quite got to yet. Okay? This region out here, though, this is the region where the fit was so bad that it actually prefers new physics living here compared to excluding it in that direction there. And you can do this for lots of things, like for instance, left-handed and right-handed SLEPTONs, we're able to make these complementary bounds to CMS. CMS couldn't say anything about a single right-handed SLEPTON decaying because the cross-section is just so small. So there wasn't any bound coming from CMS. So for the very first time ever, when we put this out, we're able to show that you can actually, with right-hand SLEPTONs, get beyond the LEP limit for the first time and eke this out to about 120 GeV using this WW measurement at 8 TeV by CMS. Now, relatively soon after our paper came out, Atlas said, hey, we can put in our entire data set from all 20 inverse femtobarns. And so this contour here represents what Atlas was able to rule out. They were able to start eating into this funnel region, but you see how the curve migrates. It's going in this direction, and it's leaving the funnel because you're still stuck with similar WW kinematics. So in certain regions, we can beat Atlas by a little bit, and others, Atlas can go beyond us. But I just want to give you this power of the difference between the standard model and the new physics measurements, because you see here, this curve is with the full data set of Atlas, 20 inverse femtobarn. Our exclusions come from 3.5 inverse femtobarn with CMS, okay? So there's a lot of power to be got out of the standard model if you're willing to take the time to understand how these standard model measurements are done. So let me conclude here. I mean, I think that personally the WW cross-section is showing a trend, okay? This could all be total BS, and it might be a fluctuation, but you can think whatever you want. New physics, though, this is the only example I know of. I mean, somebody can chime up in the audience if they have something else, but it's the only example I know of where new physics can explain and fit better than the standard model itself. The Chargino explanation, where you have real W's, this should be able to be tested very soon with same sign dileptons. The stop explanation actually is a beautiful thing where you could have stops sitting right at 200 GeV. You could have natural supersymmetry, not have the same problems of this because you don't have any same sign dileptons here. And the SLEPTON explanation is very cute in the sense that it can explain more phenomena. I can get dark matter, I can get G-2, and I can get WW. This will be also, though, able to be tested by looking at, for instance, the various flavor combinations. Real W's, if I produce two W's, can decay to E mu, whereas SLEPTONs, if I produce EE or mu mu, can never decay to E mu. Okay, so this will be an interesting thing to see in the future. This shows also how, by just taking one measurement, though, it also shows where things are fitting and all the other kind of physics that has to be included. Okay, there's clear directions in QCD physics where you can improve here. And this channel, I haven't spent too much time talking about this aspect of it, and I'm sure Elliot will talk about this more when he talks about Higgs to WW specifically tomorrow. But this channel has ramifications all over the place. WW and ZZ are the most important channels to get a handle on if we want to understand what the Higgs is doing, okay? So if you have new physics that can contaminate these measurements in any way, it is a very important thing to understand. And as I said, this explanation and this explanation don't affect the Higgs to WW measurement, but I mean, you could see it in the control region. This explanation, I didn't talk about it because I've run out of time. This one actually is very interesting. It affects the signal and control regions of the Higgs measurement differently. So what you'd extrapolate for your signal strength would actually be different that comes out of this. But of course, this also would manifest in same flavor versus opposite flavor measurements of Higgs and WW. So you can have all these kind of ramifications all over the place. And last but not least, as I said at the very beginning, I encourage you to look at the other measurements that Atlas and CMS make. Don't just spend your time getting the prepackaged stuff that gets sent out to you. If you're interested in supersymmetry, don't just look at the supersymmetry plot. Understand what the standard model does, because you're going to understand a lot more physics that comes out of it. There's a ton of physics that goes into this, and you can understand where new physics can actually be a lot better. So this was just an example, but hopefully this can encourage all of you that there really could be new physics right around the corner, and do your work to understand these things. So thanks.